Okay, and now Serena, go ahead and take it away, and thank you very much.
Great. Thanks so much. Thank you all for being here. So yeah, today I'm going to be presenting modeling pandemic behaviors with large-scale networks and machine learning. So to begin, I don't really need to tell this audience this, but we care a lot about human networks. Human networks form the foundations of our society. And these networks define individuals or groups of individuals as nodes, and they allow us to capture our diverse relationships with each other. So for example, you can maybe capture who is friends with whom, or also who comes into contact with whom. So that's physically maybe passing each other on the street or sitting at the same restaurant. And you can also capture indirect relationships, like who consumes the same news or who buys the same products. And I'm going to pose to you that many of the biggest societal challenges that we face today are driven by these human networks. As one example, pandemics are driven by human contact networks. So if an individual is infected, then they have some probability of infecting their contacts, and then their contacts have some probability of infecting their contacts. And so this contact network modulates the spread of the disease and the course of the pandemic. And pandemics, as you know, have enormous costs on lives and livelihoods, and governments have invested trillions of dollars in responding to pandemics. And so if we can better understand human contact networks and how diseases spread over them, then we can make progress on not just responding to pandemics, but hopefully preventing future ones. As a second example, supply chains are also a major priority of governments in the US and beyond. Supply chains are fundamentally a network problem because you can model them as a network of firms, and then the edges between the firms represent buying and selling relationships between them. If we want to understand challenges like supply chain disruptions, then we need to understand the structure of the supply chain network and how disruptions propagate through it. Today, I'm going to be focusing on the pandemic, but we also have some recent work on supply chains and happy to talk about it later if you have questions. So human networks also drive many other societal challenges, such as political polarization, transportation infrastructure, segregation in cities, recommender systems, and so on. And so in all of these settings, effective decision-making relies on understanding these human networks. But there's several challenges to understanding human networks and their relationship with decisions. The first challenge is we need to understand, how do these networks actually look? So what is their structure? How do they evolve over time? And the challenge is that human networks are rarely fully observed in data. For example, we don't know who exactly is coming into contact with whom or who is friends with whom. And so the data sources that we do have often provide networks at either an overly coarse level or incomplete, so maybe systematically missing certain populations. So given this sort of partial data, how do we infer the missing pieces and make the best use of large-scale network data? Second, once we have the networks, then we need to understand how processes unfold over networks. So for example, how do diseases spread over contact networks, and then use those processes to inform decisions. The challenge is that these processes can be very complex. So for example, when diseases spread over contact networks, transmission rates can vary depending on different types of contact. And so how do we get a faithful model of these processes? And third, since these are real-world human networks, they aren't static. And so they respond to decisions and policies, sometimes in unexpected ways, which means we need to not only understand how networks shape decisions, but also how decisions shape networks. So you've got a bit of a feedback loop going on here. The challenge is that estimating the causal effects of policies is hard. We can't run randomized experiments where we randomly assign policies to regions. And so we often have to estimate these causal effects from observational data. And for those of you who have worked with observational causal inference, the networks further complicate causal estimation since they often violate classic assumptions of causal inference. And so in my research, I've addressed each of these challenges with new methods. To address unobserved networks, I've developed statistical methods, and for fine-grained networks from aggregated data, I've developed methods of propagation over networks, both mechanistic models in the disease context and graph neural networks for supply chains. And finally, I've extended causal inference methods for observational data, observational network data, so that we can estimate the effects of policies on human networks. So for today, I'm going to focus on COVID-19 as a concrete application so that we can go through each of these challenges and talk about some solutions to them. So in the first part of my talk, I'll talk about network inference and specifically the problem of inferring fine-grained mobility networks from location data. Second, I'll talk about how we integrated our mobility networks into a new EPI model, which allows us to realistically simulate the spread of COVID. Third, I'll discuss how we translated our research into direct policy impact. So this includes deploying our model as a decision support tool for the Virginia Department of Health, and separately evaluating the causal effects of California's pandemic policies, including the unintended spillover effects. And finally, with the remaining time that I have, I'll tell you about some related recent work on vaccines. And so here we're using search logs instead of mobility data, but we similarly leverage graph-based methods for pandemic response and policy insights. So without further ado, I'll begin with our paper that was published in Nature, which I co-led with Emma Pearson, Pongwei Ko, and other amazing collaborators. And so, as we discussed, infectious diseases like COVID, they spread through the contact network between individuals. And so understanding this contact network is crucial for pandemic response, especially early in the pandemic when most policy interventions were focused on limiting contact. So for example, understanding contact is crucial to understanding how do we reopen safely, because the risks of reopening each place depends on how many people are coming into contact at those places, in what proximity, how long they're visiting, etc. Understanding contact is also essential for combating health disparities, because these contact patterns can both create and exacerbate health disparities. The challenge, as mentioned before, is that we usually don't know the true contact network between individuals, since we don't track who is coming into contact with whom. So if we don't know the true contact network, what can we do instead? Prior work has tried to get around this by, for example, maybe assuming the graph structure. So maybe you assume complete and uniform mixing within regions, or you model contact at a much coarser granularity, like airline networks where you do actually have the data, but these approaches miss important heterogeneity at local levels. Another option is to add many parameters to your epidemiological model, like transmission rates for every neighborhood, to make up for missing the contact network. But the issue with this approach is that data to fit these models is scarce. And so models with many parameters tend to overfit on the available data and have trouble with generalization and identifiability. So our solution instead is to infer fine-grained mobility networks directly from the aggregated location data and to use these networks as proxies for contact. And our basic premise was this: if you can successfully infer these complex, fine-grained networks from data, then your model can be quite simple. The networks will absorb much of the complexity of disease spread so that you no longer need so many parameters, but you can still accurately model the spread of disease. So this brings me to the first methods part of the talk, which is how do we infer these fine-grained mobility networks from data? In our network inference problem, ideally we want hourly visits from people to places so that we can model the spread of infection based on who is visiting where at the same time. But most location data doesn't provide such fine-grained networks. At best, we have some aggregated visits over neighborhoods and places. So for example, in our work, we use data from SafeGraph, and SafeGraph data is aggregated to the level of census block groups, or CBGs. These are local neighborhoods of 600 to 3,000 people. And they also provide visit counts for points of interest, or POIs. These are public locations like restaurants, grocery stores, gas stations, and so on. And SafeGraph has the individual GPS pings, but they provide aggregated data in order to preserve privacy. And so given this data, we want to keep it aggregated, but we want to reconcile the total number of visits at CBGs and at POIs, so we have the full network of visits from CBGs to POIs. Specifically, we're trying to infer this bipartite network that tells us in every hour how many people from each CBG visited each POI. And so from SafeGraph, we have the hourly number of visitors to each POI, and we also have the hourly number of people from each CBG who are out of the house and visiting POIs. And SafeGraph also computes monthly estimates of where each POI's visitors are coming from in terms of their home CBGs. So this does give us the network that we want, but at a monthly instead of an hourly granularity. So a key insight is that we can use an algorithm called iterative proportional fitting, or IPF, to reconcile these two data sources so that we can infer hourly CBG POI networks.
Mm.
And to take a step back, IPF is a classic statistical algorithm. You may know it by other names like Sinkhorn's algorithm or by proportional fitting. And so IPF takes as input an initial matrix, target row marginals P, so that's what you want your rows to sum up to, and target column marginals Q, that's what you want your columns to sum up to. Then IPF solves or tries to solve the matrix balancing problem, which is to find diagonal matrices D0 and D1 such that scaling X by D0 and D1 matches the marginals. And so IPF learns D0 and D1 by iteratively scaling the rows and then the columns of the matrix. Specifically on even iterations, we're going to scale the rows to match the row marginals. And so we're adjusting D0 so that we match P. And then on the odd iterations, we use the latest version of D0 and then scale the columns to match the column marginals Q. And so you basically go back and forth, adjusting D0 and D1. And it's known that if these iterations converge, the fitted matrix that IPF returns will match the target marginals. But another really nice property is that they will be otherwise as similar as possible to the initial matrix in terms of minimizing the Kullback-Leibler divergence or KL divergence to X. And so our idea is that we can formulate our network inference problem in terms of IPF. We have the hourly visitors from the CBGs into the POIs, which act as the target marginals, and we can treat the monthly network as the initial matrix. And so then using IPF, we can infer hourly CBG POI networks where the hourly networks match the hourly visitors, but otherwise remain as similar as possible to the monthly network in terms of minimizing KL divergence. And since the methods here are a bit dense, I'm going to dive into them a bit more and tell you about a recent paper published in ICML that's about using IPF for this network inference task. So first, in this paper, we recognize that the problem I just described with safe graph data is really a more general one. So that's one where you want to infer a dynamic network from what we call its three-dimensional marginals, meaning its time-varying row sums, the time-varying column sums, and the time-aggregated network. And beyond mobility, this problem could appear across domains where it's easier to observe marginals over time instead of the interiors of the network. So for example, in transportation, you might observe swipes coming into and out of subway stations, but it's harder to observe the paths that people are taking from one station to another. Or in migration, you might observe inflow into regions and outflow out of regions, but you don't quite know where people are moving from or to. And so IPF poses an attractive method to use in this setting because it also deals with marginals. But IPF has been mainly used in matrix balancing, where the goal is to fit the target marginals, but there's no explicit network that you're trying to infer. And so the goal of this work really is to ask, why is IPF a good idea here? And more specifically, under what model is IPF a reasonable estimator of a dynamic network from its marginals? And in our work, we answer this question by finding a generative network model where IPF in fact recovers the maximum likelihood estimates of the network's parameters. So in our model, we have a time-varying network xt, which is a scaled version of the time-aggregated network x bar, drawn from a Poisson distribution, and each entry is scaled by a parameter for the row, which is ui, and a parameter for the column, which is vj. And in this model, we observe the time-aggregated network x bar, but we don't observe the time-varying scaling parameters or the time-varying network. What helps, though, is that we do observe the marginals of the time-varying network, meaning its row sums and its column sums, and we show that these marginals form sufficient statistics for the model. And so our main result is that under this model, IPF recovers the maximum likelihood estimates of the scaling parameters u and v. And I'll skip the proof for now, but the basic idea is that the log likelihood of our model is equivalent to the dual of the KL divergence problem implied by IPF. And I can point you to the paper as well. But for now, let's discuss some implications of this result. And so first, we've answered our question. We found this model under which IPF is a reasonable estimator for inferring a dynamic network from its marginals. Specifically under this model, IPF returns the maximum likelihood estimate of the network parameters, and we should actually interpret IPF as trying to estimate the expected values of the hourly network. And second, our model reveals implicit assumptions that we're making about the network when we use IPF to infer it. So for example, IPF is most justified if you can say the expected values of the time-varying network are only a rank 1 modification of the time-aggregated network, and also that each value is sampled independently following a Poisson distribution. And so since this network problem appears across domains, it's valuable to make these assumptions explicit so that practitioners can evaluate whether these assumptions make sense in their domain. And finally, our network model enables several new analyses of IPF. For example, we can quantify uncertainty in the parameter estimates, which is not provided by the IPF procedure. We can also evaluate IPF's estimation error on the true network parameters instead of only on the target marginals. And we can also test IPF's performance under model misspecification now that we have an explicit model that IPF works under. And so our paper also includes other results, such as an algorithm to enable IPF iterations to converge, because we do observe non-convergence sometimes when we are using sparse real-world network data. So happy to talk about that too. But for now, let's come back to the application and where we paused. So we wanted to use IPF to infer hourly CBG POI networks from aggregated location data, and now we have that justification. So we applied IPF to infer hourly networks in 10 of the largest metropolitan areas in the US from March to May 2020 in the first wave of the pandemic. We talked a lot about the theoretical properties of IPF, but one of its empirical advantages is that it's very lightweight because the row factors can all be computed in parallel, and so can the column factors. And so we're able to infer these large-scale networks with 500,000 POIs, 57,000 CBGs, and 5.4 billion hourly edges. So we also released our networks in agreement with SafeGraph. I'm happy to point you to them if you're interested. They've been downloaded by hundreds of researchers and used in various follow-on studies. So this concludes the network inference part of my talk. Now we're going to talk about how do we use these networks to model disease spread and to analyze different strategies for pandemic response. And so we integrate our mobility networks into an epidemiological model. I'm going to go over the SER model quickly because I assume several people in the audience know it already, but we use the standard compartmental design where we assume that individuals can be in one of 4 disease states: susceptible, which means they can get the disease; exposed, which means they're infected but not yet infectious; infectious, which is what it sounds like; and then removed, which means they can no longer be infected or infectious. In our work, we were just modeling the first wave of the pandemic, and so we don't consider going back from the removed to the susceptible stage. We assume that people just progress through the 4 and end up in removed. But in later work, it would be interesting to also explore an arrow back to susceptible. And the key to our model is that we maintain disease states for each CBG. So those were the neighborhoods. And then we use the mobility network to determine how people across CBGs come into contact. And if they come into contact at the same POI, then there is some probability of them infecting each other. And so one thing to note is we can also model POI-specific probabilities of infection, and those depend on the POI's area in square feet, the median dwell time, the number of infectious visitors, and current levels of mask wearing. So most of these come from external data, and infectious visitors is endogenous to the model. So in summary, our work can be described by this pipeline. So first, we infer the mobility networks from the aggregated location data. Then our networks, along with many other ingredients, go into our epidemiological model. We learn the free parameters of our model by fitting it to reported daily case counts, and then we use our fitted model to conduct all sorts of analyses. I wanted to note that incorporating so much real-world data means that our model can actually be very simple, which, as you remember, was our original premise. So our model actually only has 3 free parameters, literally 3 numbers, and these are fixed over time. Despite that, we are still able to fit all sorts of case curves during the first wave of the pandemic. So here, the blue line represents our model predictions, and the orange line represents reported daily cases with weekly smoothing. So our simple model is able to fit linear trajectories like in Chicago, but it can also fit harder curves like cases that plateaued like in Philadelphia, or even those that went downward like in New York. And this shows the power of our mobility networks since they enable our simple model to fit complex case curves. And we conducted various robustness and ablation studies as well, showing that the networks are really what allows the model to fit well. And for example, if you aggregate over the network and simply provide an hourly time series, the model does not fit as well. So now we have this model, what can we use it for? So first, we use the model for retrospective analyses. And this is meaning that our model realistically simulates who got infected, where, and when, down to the CBG, the POI, and hour. And so this allows us to analyze disparities in risk, like which CBGs were the most at risk, or which types of POIs were the riskiest to visit. Second, we can use the model for forward-facing experiments. So the idea here is our model takes in the series of interpretable inputs. And so we can modify any of those inputs and run the model forward to see how predicted infections change. To demonstrate these capabilities, I'll go over 2 example use cases. So first, we used our model to test a partial reopening strategy, where we reopened all POIs, but we capped visits to some percentage of the POI's maximum occupancy. And then we evaluate the reopening strategy based on 2 objectives. So on one hand, we want more visits, since those serve as a proxy for the economy, businesses, and consumer goals. But on the other hand, we want to minimize infections. And so, as expected, these are competing objectives, since more visits lead to more disease spread and infections. But the exciting result is that the relationship is highly nonlinear, meaning a small reduction in visits can lead to a large reduction in infections. So for example, if we use a 20% occupancy cap, then we lose around 40% of visits, but we reduce predicted infections by 80%. This strategy works well because it disproportionately reduces visits at POIs during their high-density, risky hours, but it allows businesses to return as usual everywhere else. We can also use our model to analyze health disparities. And what was remarkable was that our model correctly predicted socioeconomic disparities without demographic information. And so when we ran our model on the CBGs, it didn't know which CBGs were lower income or more heavily minorities. But based on the mobility networks alone, it correctly predicted that lower income and minority neighborhoods get infected at higher rates. And so then we wondered, how is the model able to predict these disparities solely from the mobility networks? And we found that there were 2 reasons. So first, lower income and less white CBGs were not able to reduce their mobility as much. This could be because they're disproportionately represented in essential jobs and less able to work from home. But second, it's not just how often people go out, but where they go. And we found that people from lower income and less white CBGs tended to visit POIs that were smaller, more crowded, with longer visit times, and therefore riskier under the model. For example, we found on average that one trip to the grocery store was 2 times riskier for someone from a lower income CBG compared to someone from a higher income CBG. And these findings reveal that mobility could be playing a substantial role in why we see demographic differences in infection rates, which informs how policymakers tackle these disparities. So when we released this work, we were excited that the findings reached broad audiences. We received coverage from over 650 news outlets, including an interactive article in the New York Times. Our work was also cited by various institutions and governments around the world. For example, here you can see one of the figures from our paper that was remade by the Office of the Prime Minister in Poland to be printed in a Polish newspaper. We are also cited in 2 amicus briefs for the US Supreme Court and by the CDC, New York Times editorial board, and US Joint Economic Committee. Given this attention, we wanted to actually translate that into direct policy impact, which I'll tell you about now. And so we wanted to directly support policymakers with decision support tools. To do this, we partnered with researchers at the University of Virginia who are advising the Virginia Department of Health on pandemic policies. They reached out to us because the department had a need for data-driven tools to assess potential reopening plans. And so together, we transformed our model into a new dashboard that allowed the Virginia Department of Health to test thousands of different reopening policies so that they could analyze trade-offs between predicted infections and mobility. And creating this dashboard required substantial effort, such as new features, a new computational infrastructure, and new visualizations based on our discussions with the department. And so in recognition of these efforts, the paper won the Best Paper Award in KDD in the Applied Data Science track. But finally, one question was, one thing that we weren't able to capture at the beginning of the pandemic was how people actually respond to mobility restrictions. For example, in our original model, we assumed that if gyms were closed, then people simply wouldn't go to gyms. But one complication with this theory is when neighboring regions have differing policies. So, for example, maybe you have one county that's under lockdown while its neighbors are opened. And so, in that setting, do you see people spilling over from more restricted to less restricted areas? So, this brings me to the final paper in this section, which I'll discuss just briefly. This paper was published recently in AAAI. And in this work, our goal is to estimate the geographic spillover effects of local policies, but there are many challenges to estimating these effects. So first, we can't run experiments where we randomly assign regions to different policies. Second, since spillovers arise specifically when regions have their own local policies, then each region might have its own definition of a policy or how they're assigned, which makes it difficult to identify a consistent treatment for causal inference. And finally, one of the biggest challenges in these observational studies is confounders. So, for example, if you want to estimate the effect of a COVID policy on mobility, then COVID severity serves as a confounder because higher COVID rates could both predict more restrictive policies, but also people might reduce their mobility on their own because they're scared of COVID, but you can't attribute that reduction to the policy itself. And so our goal addresses these challenges. First, we identified a unique policy setting, which is the California Blueprint for a Safer Economy, that lends itself to natural experiments. In this setting, all 58 California counties were assigned to tiers based on cutoffs of COVID metrics like case rate or test positivity. And each tier represents a bundle of mobility restrictions from most to least restrictive. So this setting was quite ideal because the tiers are defined in the same way across all 58 counties, but the tier assignments can be different at the same time. So that can incentivize spillovers between counties. And furthermore, because these tiers are assigned at the predetermined cutoffs of COVID metrics, then we can use regression discontinuity design or RDD to estimate local unconfounded spillover effects. I'll skip the explanation of RDD for now, but happy to explain if there are people in the audience who want to know what it is. But under this RDD framework, we can estimate spillover effects by fitting the model to the mobility network so that we can learn the spillover effects. And so using our model, first, we found significant spillovers from more restricted to less restricted counties with larger effects in retail, gyms, and eating places. And so this heterogeneity could both reflect what people are willing to travel for and also what the tiers are restricting. So for example, grocery stores generally stayed open under all tiers, so there is no reason to travel for them. Second, based on our fitted model, we compared county level restrictions to statewide restrictions in terms of how much they reduce mobility. And so this is under our simplified model, so take this with a grain of salt, but we did find a substantial difference between the two settings, with county level restrictions being only 54% as effective as statewide restrictions at reducing mobility due to these spillovers. And this demonstrates the importance of taking spillovers and other sort of strategic behaviors into account when you're doing policy planning. And thinking, as we said at the beginning, about not only how networks shape decisions, but also how decisions shape networks. So this concludes my main story for today. To summarize some contributions, first we talked about network inference, where we developed this theoretical basis for using IPF to infer dynamic networks. Then we applied IPF to the large-scale mobility data so we could infer mobility networks. Second, we developed a new epidemiological model that integrates our mobility networks so that we can then analyze reopening trade-offs and study the impacts of mobility on disparities. And third, we translated our model into direct policy impact by designing a decision support tool for the Virginia Department of Health. And then we analyze the actual impacts of policies by studying spillover effects and the trade-offs that they induce. So with the remaining time I have, I want to switch gears a little. So far, we've talked about mobility data. And I think of that as, so mobility data is an example of data that we can get from cell phones and other wearable sensors. And I think of these types of sensing data as extremely useful when you want to know what individuals are doing. And so, for example, we want to know how much are people socially distancing, or what kinds of places are they visiting. But if we want to understand and predict behaviors, we can't just look at what individuals do. We also need to understand how do they arrive at that conclusion? What were they thinking that they then led to those sorts of behaviors? And so in this part, I'll describe a new type of data, search logs, that gives us a window into what people are thinking and feeling. And I've also worked with other sources of social data, such as speeches and social media, that are quite useful in this regard as well. So this is recent work on search logs, joint work with Adam Forney and Eric Horvitz at Microsoft Research. It was recently accepted to Nature Communications. So this work begins with the fact that vaccine hesitancy remains a key public health challenge in the US and beyond. So for example, by July 2021, several states still had 40 to 50% unvaccinated, even though adults were eligible by April 2021. So to address vaccine hesitancy, policymakers need detailed vaccine data. They need to know who has and hasn't been vaccinated so that they can allocate interventions efficiently. They also need to know why people are holding out so they can best address concerns. But the issue is that these data in the US, and I'm sure in other places as well, are currently insufficient. And so we have reported vaccine rates, but they are often delayed. They're also often missing below the county level and missing important demographic information. We also have vaccine surveys to try to understand hesitancy, but those usually only cover high-level topics, and they might be prone to self-reporting biases because people are reporting their answers themselves. And so to fill these gaps, we propose large-scale anonymized search logs as a complementary data source. And our idea is that we can answer both of these questions from search logs. So first, we can use search logs to detect who is seeking a vaccine and estimate fine-grained vaccine rates from these signals. And second, we can discover vaccine concerns directly from the search logs of vaccine holdouts, which allows us to overcome these self-reporting biases because we're looking at revealed behaviors. And so let's start with the first task, where our goal is to detect vaccine intent, specifically when a user is trying to get the COVID vaccine on Bing. So let's say you're a user. How might a user show intent? If she queries COVID vaccine, she might be trying to get the vaccine, but she might also be trying to get general information about the vaccine, like eligibility or how effective it is. But if she queries COVID vaccine near me, that's a lot more suggestive that she's trying to get the vaccine right now. Or similarly, if she queries CVS COVID vaccine or any other pharmacy name, she's probably trying to get the vaccine at that pharmacy. And so for queries like these, we find that regular expressions actually do suffice for separating the vaccine intent queries from all of the other ones. But we shouldn't rule out the first query entirely yet because she could still clarify her intent through clicks on search results. So for example, if she then clicks on the CVS registration page for the COVID vaccine, then we could also infer that she has vaccine intent. And we do find that for clicks, we need more sophisticated methods than regular expressions because URLs don't follow such formulaic patterns. And so to identify URLs, we construct what's called query click graphs. This is another bipartite graph where now you have queries on one side and URLs on the other side, and an edge from a query to a URL represents how often this query is followed by a click on this URL. And so then our key idea is that we can propagate labels from the query side, which are labeled with regular expressions, onto the unlabeled URL side, so that we can automatically discover URLs that are likely to be vaccine intent. That's the basic idea. Specifically, we do this in a three-step process. So first, when we don't have any URL labels, we use personalized paging, which I'm sure you're familiar with, to propagate labels from the queries to the URLs. Then using personalized PageRank, we now have a ranking over URLs, and we present the top ranking URLs to annotators on Amazon Mechanical Turk, and we gather a small number of labels for those URLs. And then finally, since we only had a small number of manual annotation, then we also train graph neural networks on the URL labels, as well as the original query labels, so that we can expand the URL set by an order of magnitude while maintaining very high precision. And so that's the three-step process. To go into the GNN, or the graph neural network step, a little bit more, the goal here is to train the GNN to predict whether the URL is vaccine intent or not, and then to use the GNN to discover new vaccine intent URLs. And so we introduced two methods that allow our GNN to achieve stronger performance so that it can achieve strong performance across all 50 states with AUCs above 0.9 and precision above 0.9 in all 50 states. And these two methods are, first, we do a little bit of pre-training, and second, we have a specific way of how do we discover new URLs once the GNN is trained. The more important metrics, though, are that we can actually improve our coverage, meaning how many users we detect with vaccine intent. And we find that each step of our pipeline improves our coverage from only using queries to adding the manual URLs from Amazon Mechanical Turk to adding the GNNs and the expanded URL set. And so with our full classifier, we identified 7.45 million users that showed vaccine intent, which is 2.3 times the number of users that we detected with only queries. In addition to coverage, we also evaluate our classifier's correlation with reported vaccination rates from the CDC. That's the Center for Disease and Prevention in the US, that's releasing vaccination rates and also responsible for a lot of pandemic control. So we find that each step of our pipeline also improves on the CDC correlation, and our full classifier achieves a strong correlation of 0.86 over states. We also apply corrections to account for non-uniform bin coverage, and these corrections also improve our correlations. We also evaluate at the county level and also at the zip code level. We also find strong correlations over time. So if you allow the CDC time series to lag our time series by 7 to 15 days, we can achieve a max correlation of 0.89. That's a median over the states with varying lags per state. And this lag demonstrates the real-time advantage of search signals because we don't have to wait for delays in vaccination or vaccine reporting. And so that's why the search signals precede the CDC reporting by 1 to 2 weeks. So now we have this classifier. We're going to first use it to estimate vaccine intent rates per zip code. And so zip codes are a small granularity in the US. It's usually used as a postal code, and they're 10 times the granularity of counties, which is the finest grained vaccine data that the CDC releases. And our release data represents the largest existing COVID vaccine data set at the zip level, and you can find it online. We can also use our classifier to identify vaccine early adopters and vaccine holdouts. So we define early adopters as those who showed vaccine intent before April 2021, and holdouts as those who didn't show it until July. And we think that waiting until July indicated holding out because all adults were eligible for the vaccine by April 19th. So first, we find that holdouts, when we compare them to early adopters who are matched to them on covariates, they are 67% likelier to click on untrusted news. So here we get news scores from NewsGuard, who's a third-party source that has labeled different news sites for how trustworthy they are, providing a score from 0 to 100, meaning more or less trustworthy. And when we compare to these labels and then we use the holdouts versus the early adopters, we find that holdouts are significantly likelier to click on untrusted news, and you can see the relationship visualized here. We also characterize the vaccine concerns of holdouts and early adopters, and to do this, we construct a novel taxonomy of vaccine concerns on search. And so what we did was we gathered around 25,000 vaccine-related URLs that were clicked on by the holdouts and the early adopters. And then we organized those 25,000 URLs into a hierarchical taxonomy of what the categories were. And so we end up with 8 top categories, 36 subcategories, and around 150 URL clusters. And the taxonomy, as well as the URLs, are also released online. I think they can be used for other research, such as social media, if you want to understand, for example, the diffusion of news on social media with labels for what kind of news is being diffused. So importantly, the granularity of our taxonomy allows us to discover nuanced differences in the concerns of vaccine holdouts versus early adopters. So for example, we find that both groups are concerned with vaccine safety, but you can see from the bolded subcategories, vaccine holdouts are most concerned with eerie fears, which are these debunked myths, such as believing that the vaccine might turn you magnetic or insert a microchip in you. So unsurprisingly, they're most interested in eerie fears, but they're also far more interested in FDA approval. So whether the vaccine was approved by the FDA, as well as vaccine-caused deaths. So that's thinking that the vaccine causes deaths. They're very interested in vaccine development, which is, the speed at which the vaccine was developed and whether it's gone through all of the checks, as well as some concerns around reproductive health. And they're slightly more concerned with severe side effects. And early adopters are much more concerned with what's called normal side effects and severe side effects. And so normal side effects are, like, will my arm turn sore? Severe side effects are things like blood clots. So plausible, rare, but plausible. Another interesting result is that when the holdouts finally express vaccine intent, we witness a significant change in their vaccine concerns. And so as they approach vaccine intent, we see that their concerns nearly reverse, such that they look much more similar to the early adopters than their typical selves. So you can see this reversal between the two slides, right? Like the bars almost reverse. But the holdouts don't adopt all of the early adopters' concerns, though. So for example, they seem more interested in the Johnson & Johnson vaccine than the mRNA vaccines, and they remain uninterested in things like general vaccine rate statistics. And our hypothesis is that there are some interests that are very topical that have to do with trying to get the vaccine, like comparing different vaccines. That's one that we see both of them very interested in, close to their vaccine intent. But other interests are more of a personality interest, like an interest in general vaccine rate statistics, like how vaccinated is Japan, how vaccinated is Australia. Those kinds of statistics only early adopters are interested in, and holdouts, even as they approach vaccine intent, are not that interested in that. So these findings suggest that individuals possibly go through similar, although slightly different trajectories of vaccine concerns as they approach vaccine acceptance. And we hope that future work can develop models of these dynamics, especially to understand key influences that move individuals from one phase to the next, because then you could maybe, with the proper privacy protections, try to allocate, for example, a limited budget of interventions so that you are intervening with, for example, online campaigns. You're intervening on people who are just about ready to move on to the next phase, just about getting closer to vaccine acceptance, instead of people who are, very holdout and not going to be moved. And so since we're dealing with sensitive data in this work, I also wanted to mention some thoughts around data ethics and availability. We're very careful with how we use the data. First, we obtained approval from Microsoft IRB and the Bing product teams. We also only use anonymized search logs, and those can't be linked to other products. We only use individual information wherever necessary. So for example, individual search logs, but we leave other user information like their location or their demographic. We leave that to zip level accuracy, and we don't try to link to other Microsoft sources like browser information. And finally, we only report results aggregated over thousands of individuals. But certainly when you do this kind of work with search logs or mobility data, you really have to constantly think about the balance between the utility of the results that you might derive and the risks to privacy or the thoughts on data ethics. And so I think a good principle is to only use the data that is necessary and don't use anything more than that. Other data sources we use, besides Bing, are CDC rates, US Census data, NewsGuard labels, and so on, which are publicly available. And you can also find our released data and code on GitHub, and that includes the zip level vaccine rates, as well as our taxonomy of vaccine concerns. So some final concluding thoughts. Certainly, like, data sources are still imperfect. Beyond the questions about data ethics, there's also just the fact that the data is imperfect. Mobility data doesn't cover all populations, for example, children, and Bing doesn't cover all individuals or types of vaccine seeking. So you might miss like a walk-in appointment because it didn't show up on search. Another limitation is that the models are certainly imperfect. So for example, the SCIR model makes simplifying assumptions. We didn't include, for example, asymptomatic transmission or differences within the census block group, although those are very small. Vaccine intent classifiers. So our vaccine intent classifier is query and click level. So it's not session level. You could imagine coming up with a more sophisticated classifier that looks at the collection of all of the queries and clicks during the session instead of just one at a time. We didn't do that for simplicity and also for privacy reasons, it would be much harder to get annotators on Amazon Mechanical Turk to label sessions as opposed to individual queries and clicks, which can be not seen as individual, like from an individual, because, for example, a click on a URL, these are public URLs. And so it's not that you're not sharing that much about a person to say that they clicked on the URL. Whereas if you have the whole session, it's much likelier that you can't anonymize it so effectively. And then also, of course, the classifier is going to miss some true intents, some true vaccine intents, because there could be these edge cases where people show vaccine intent through certain URLs or queries that we missed. With that, though, our resources still achieve strong performance and derive these important policy insights that we couldn't have had otherwise. And so in the first set of papers that I showed you, we had mobility data, we had the network inference with IPF, and then we had the SCIR model. Putting these together, we now enable these accurate fits of real COVID cases, even though the model itself is very simple. And then we can also study who got infected where and when, which informs reopening and disparities. In the second paper or the second story that I showed you, we have search logs, and then we combined it with the vaccine intent classifier, including these deep learning methods like graph neural networks. And that allows us to achieve AUCs above 0.9 and strong correlations with CDC rates. And with the classifier, we can now get fine-grained real-time monitoring of vaccine rates and concerns, which can hopefully improve vaccine interventions. And so this was all my work on the COVID pandemic, but I've also done work with networks and big data in other settings, including polarization and politics, as well as supply chains, which I mentioned a bit earlier. So happy to talk about those as well. With that, I'll conclude for today. This was modeling pandemic behaviors with large-scale networks and machine learning. You can check out my website. Feel free to email me, and I'm happy to take questions now. Thank you.
Great. Thanks so much, Serena. There was one question a while ago in the chat. It's a
Yeah.
bit out of context now. I don't know if
Oh,
Prathuj,
I'm happy to go back.
yeah, I don't know, Prathuj, if you want to ask that question out loud if you're still here.
Oh, yeah, that would be
Yeah,
easier.
I can just point where it was. Like, so it's in the part one, I think at the end
Yeah.
of the part one of your talk.
Okay, great. Okay. Sorry. It might actually be faster if I go from the side view. End of part one, you said?
Yes.
Okay.
So
Like
it's
around
maybe a kind of phase transition you're mentioning in the um
Is
in
this the network inference part one or like the overall part one around like mobility networks?
it's about the mobility networks. Yeah.
Okay, okay.
It's a,
So maybe I should, is this the right slide, the one that I'm looking on?
yeah, I think a little after
A
38,
little
like
left.
somewhere around
Okay.
40.
Or is it something like this?
Yeah.
Or
Yeah, I think this is the one. Yeah. 47 or 47 if I'm not wrong.
47? Oh, 47. Oh, here, this?
Yeah, so here I think, yeah, the small reduction in visits, I think that's the part I
Yes,
was
that's right. That's
asking
right.
about.
Yeah.
Like,
Mhm.
do you observe any phase transition there, and is it commonly a recurring thing that you see a phase transition for at that point?
I see. You're saying like all of a sudden the curve will just yeah.
Yeah,
Um yeah, I mean you can see the curve right here. I think there's nothing I think as extreme as a phase transition, but you
yeah,
definitely do see that the curve is nonlinear and it's clearly concave. And so what this is saying is, for example, like if you use a 20% occupancy cap, you lose 40% of visits, but you can reduce infections by 80%. If you use a 30% occupancy cap, then you lose 25% of visits, but you reduce infections by 64%. So I don't think there's anything as extreme as a phase transition, but certainly you do get these nice big gains for small
yeah,
costs. And the reason for that is because a lot of POIs are not reaching their maximum occupancy or even 20% of it. And so
Okay.
for those POIs, you can just return visits as usual for those POIs. But then you can cap visits when POIs are going above that occupancy cap. And that's when POIs are in their are in their riskiest hours. And so that's when they're going to cause the most infections. And so if you can strategically take away visits from the riskiest POIs while otherwise returning visits, then you get a lot of visits back while still reducing infections by a lot.
Thank you. Yeah, that's helpful.
Yeah.
Thanks. I had a question also, and if anybody else does, feel free to raise your hand. My question was about kind of a tangential project. I'm wondering if it's
Mm.
going on in terms
Yeah.
of Bing itself. So you're looking at search logs. So
Yeah.
I imagine you can't see what the user saw when they put in a search. You can
Mhm.
only see the things they clicked on.
Yeah.
Presumably Bing does lots of personalization of search, just like Google
Mhm.
does. So I was wondering if there's a way through this search log to see if Bing's, say, ranking of
Yeah.
pages is having
Yeah.
any effect, or any kind of personalization they're doing is having an
Yeah.
effect on how people are, which things they ultimately click on. Um,
Yeah.
yeah.
Yeah, I think that's a great question. And especially if you're thinking in these like sensitive contexts like vaccines, someone can look up some sort of query that's ambiguous. Maybe it's like keying towards some sort of misinformation, but then the search engine is definitely deciding how it wants to rank the, like maybe it has a more trusted result that is less directly relevant to the query versus something that might be more misinformation, but it's clearly like what they were looking for. And so how do you decide between those rankings? I think that's really interesting. We didn't explore the ranking or personalization as much. I think another nice idea there is maybe you could try to get some causal estimates. I didn't do this in this work, but I have seen prior work before that exploits slight randomization in the ordering of the ranking. And so then you can try to say, like, what is the causal effect of ranking this a little bit higher on some downstream outcome? And normally it's really hard to get these causal estimates. It's very confounded. If you see that like a user clicked on a misinformation URL, like you don't know if it's because of that URL that they made some later on decision or because they already had some latent misbelief in the vaccine, so they clicked on that URL and then they didn't get the vaccine. And so if you can exploit randomness like from the ranking, I think that's quite powerful.
Thanks.
Yeah.
Bernardo?
Hi. Thanks.
Hi.
Thanks so much for the talk. Really interesting.
Thank you.
So I had a question about the spillover effect when you were looking at the California
Yeah.
example specifically.
Yeah, let's talk about it.
So do you have a feel for when individual counties were
Mm.
changing the restriction levels over time, whether those trends were more or less synchronized between counties that were adjacent? Because I'm
Yeah.
thinking in
Mhm.
terms of
Mhm.
if you have high numbers of cases
Yeah.
in one county, are
Yeah.
you more likely to also see high numbers of cases in surrounding counties and therefore to see sort
Yeah.
of the reopening going at similar paces? And how does that translate to
Yeah.
interpreting these effects of people crossing counties for specific
Yeah.
activities?
Yeah, this is a good question. So there's like this sort of descriptive answer, which is if you look at the paper, we do have a plot that shows like how many counties are in each of the 4 tiers over time. Here. So for example, this is one such plot. So you can see like on March 15th, there are still lots of neighboring counties that are in different tiers. But red and purple are the two like most serious tiers. So yeah, for example, you're not going to see like purple, lots of purples on the map, and then also lots of yellows. That would be a little bit unexpected because those are like the most far apart tiers. I think it goes purple, red, orange, yellow. And so here you can see just like one little yellow, but mostly it's like purple and red, meaning this was a more serious part of the pandemic. As you progress through 2021, you're going to see more like reds and oranges, and then maybe like oranges and yellows. But I think you do still have a good amount of neighboring counties that are in differing, maybe like off by 1 tiers. And so in our work, we focus specifically on the purple and red boundary because there are so many of these pairs. And we look at
Okay.
them over the course of like early 2021. Um, and then to the question about how does this actually affect people's like mobility, I think I think it's interesting. I mean, I think the regression discontinuity design gets around the confounders. And I don't know, are you familiar with RDD? I can explain.
No, not particularly. Yeah.
Oh, cool. Okay, I can tell you about RDD. So RDD is this really nice, like quasi-experimental technique that you can use on observational data. And so let's take a step back from like this setting and do a more simple setting. Let's think of just like, so RDD can be applied whenever you have some sort of continuous variable and a cutoff. And so let's say, for example, there's like a test score. And so students who take the SATs, maybe if they score above 1200, then they get to participate in some like college prep program. And if they don't score above that, they don't get to. And now let's say you want to estimate what is the effect of the college prep program on college outcomes of whether you got into college or not, or what college you got into. Of course, you can't just compare the students who took the prep program versus didn't. They can be different in all sorts of ways, maybe the schools that they went to or their like socioeconomic backgrounds, etc. The key is that because you have this cutoff, this 1200, you're going to focus on students that are just above the cutoff and just below the cutoff, maybe like 1200 up to 1210 and up to like 1190. And so you focus on students just in this very narrow window of the cutoff, and then you can say the treatment was assigned effectively at random. It was due to just tiny randomness in how they took the test that day. Like, were they feeling a little bit sick, or were they feeling like, I don't know, a little tired? They didn't get a good night of sleep before. And so you exploit that randomness from the test procedure itself, and just look at students just in that margin, because you can, otherwise the assumption is that otherwise they are effectively like similar groups. And so that's the idea. So you compare just above and just below the cutoff. And the key to making RDD work, there's a couple of assumptions that must be met, but one of them is that these cutoffs must be predetermined. And they can't be gamed. Like, you can't have people who happen to be just above the cutoff because they like argued with the test practitioner and they're like, come on, like I did really well. Please like push my score up to 1201. And so you can't be able to game it, and they have to be predetermined. And so we basically import that framework over to here, where now our continuous variable are the COVID metrics. So like case positivity and test rate. And we focus on only the counties that are really close to that margin of the cutoff. And then we look at the counties that were assigned to purple because they just didn't quite make the cutoff versus the counties that are assigned to red because they just made the cutoff. And so you should interpret our spillover results as unconfounded spillover estimates, but local. And so it's local, meaning it's only for counties that are just around the cutoff. And so you can't quite extrapolate out to counties that have like crazy numbers of cases or also really low numbers of cases.
Okay, so the spatial proximity, as in whether they were adjacent or not, that was not necessarily incorporated explicitly into the RDD framework. Okay.
Yeah. We just focus on the neighboring aspect because there's more mobility between those pairs.
Okay, cool. Thanks.
Yeah, so it's not like a spatial RDD. It's actually just
no, got it. Awesome. Thanks.
Sure.
Great. And we have one question from Nico in the chat about the network inference part.
Yeah.
Assuming there's this independent Poisson sampling from the aggregated network, that depends a lot on the network itself. So how reasonable is this assumption if the time period over the aggregation has much smaller or much larger perturbations?
I see.
He hopes it makes sense, and I do too.
Yeah. So, okay, let's look at the model a little bit together. So this is our model. So the independence of the Poisson is saying each entry of the time varying network, so that's xijt, each entry of the time varying network is sampled independently from their like expected means. And so sampled independently from the Poisson variables. And so each Poisson variable is this scaling parameter for the row, scaling parameter for the column, as well as the time aggregated network. And so the independence is not actually over time, it's within the same time slice. We're saying that the entries were independently sampled relative to each other. And so I don't know if that, like, I feel like, because the question was about whether the time slices were wider or thinner, I think.
Yeah, about the size of the perturbations. Nico
besides
can
the
type whether
perfect.
that works
Let
or
me just
try
look at
to.
the typed question. Let's see. Okay. Assuming the depend a lot on the depend a lot on the aggregated network. How reasonable is this assumption if the time period over which the network is aggregated is characterized? Oh, I see. Yeah. So I think one related result that we do have, or actually, yeah, let's just talk about this offline. There is some stuff about stationarity that does come into play. And so I think that could relate to the how much the time period is perturbed and how much changes over that time period. And so I'll point you to our results on stationarity and we can talk about it more.
Great. Any last questions? Don't see any hands up. Oh, there's one. Yeah, Moritz, go ahead.
Oh, hi, Moritz.
Hi, very great talk, awesome stuff. Obviously followed your work over the last few years,
Yeah.
very related work. I have two questions. One question is with respect to validation, because you have very detailed metrics of mobility in California, but
Yeah.
ultimately you're operating on, city level
Totally.
data on numbers of cases through time.
Yeah.
And testing has been changing and all of that. So how much are you thinking about validation, contact tracing, or genomic data or other things?
Yeah.
So that's my first question. And the second one is, really fascinating the work in Virginia, building the dashboard. Can you give a little bit more detail on how it was actually used and whether you what was the feedback from the policymakers?
Yeah.
What kind of extensions are they really thinking about in
Yeah.
really deploying and using it? And I'm asking this from a perspective of sort of explainability, right? Like thinking about the very detailed model. It's very beautiful. You can say, well, if you reduce contact in hospitals or in restaurants like this, and this happens. But ultimately, it's decision makers who go on to then implement policies based on it.
Totally.
So I'd love to hear a little bit more about how that
these are good
process really
questions.
works.
I'll just have the dashboard up while I talk. So the first question was about evaluation. And I think that is just such an important question when you do machine learning for public health. It's this pretty unusual setting where I think people usually with machine learning, you're used to having just abundant data. And so like I mentioned at the beginning of the talk, the challenge here is that there's often very little data to fit your models on. You can't be training hundreds of parameters in your deep learning neural net because you might only have a time series for a single city to fit your model on, maybe 30 or 60 data points. And so that really guided our model design. For this work, for example, we didn't try to build a GNN, even though we have the tools and the ability to do that, and we do that in other works. But here it was very much more of a mechanistic model, and we tried to stick close to the data. And so that's why we have this simple model that only has 3 parameters in it, very interpretable parameters. The 3 parameters were it scales the transmission rate at POIs, and then it scales the transmission rate at CBGs, and then the initial proportion that were infected. And those are our 3 parameters. And otherwise, everything comes from either the inferred mobility networks or external data. And so that is how we tried to get around the fact that there was so little data to evaluate against. I think that's the first answer. I think on the network inference part, we weren't able to do this in the original Nature work because we didn't have the ground truth networks. But in our follow-up ICML paper, we actually did compare the networks that were inferred by IPF to ground truth hourly networks. And so this was in a setting where we actually had individual bike trips. So this was released by the city bike system in New York City. And so they release actual individual bikes. So the start station, the end station, and the time that the bike trip happened. We aggregated that up to hourly networks between bike stations. And then we gave IPF the same ingredients that we gave it in the Nature paper, which was the hourly marginals of the network, as well as the time aggregated network. And we tried that with day aggregated, week aggregated, and month aggregated. And we show that there are decent correlations between the IPF inferred version versus the ground truth hourly network. And we also can show like how quickly those correlations drop as you aggregate over more and more time. And so, for example, I think we found that the drop from day to week was a lot worse than the drop from week to month because the daily patterns are quite important. But once you get to week, you have the entire week in there. And so month doesn't actually lose that much information. And so, yeah, those are two forms of evaluation. I think the third thing is to say that the sort of insights that we're drawing from the work are not as specific as like, oh, this POI is really infectious. Like we never want to report result, or even like this CBG is super infected. It's all very aggregated. And it's these sort of qualitative insights, like a small number of visits, a small reduction in visits can lead to a large reduction in infections, or another qualitative insight like the disparities results, where we saw that lower income and higher income CBGs are getting infected at very different rates. And I think that would be true under even perturbations of the network. Yeah, okay, so that's the evaluation question. Now the dashboard. Yeah, so you wanted to know how did the Virginia Department of Health use this or interact with it. So we had a few meetings with them where we actually developed the dashboard in collaboration, like they told us what would be useful. For example, they were the ones, I don't think you can see my mouse, can you?
Oh, we can, yeah.
Oh, you can, great, okay. Do you see these little like bars around the current mobility? So for example, that was their idea. Like they wanted to know what is the range, like what the bars basically mean is saying, what is the range of mobility that we actually observe right now? And so this is saying relative to 2019 levels of mobility, how much mobility is there actually right now? And then the hypothetical that you're running is you're choosing different percentages of 2019 mobility. And so that was another change that we made from the original paper. So instead of trying to simulate, for example, maximum occupancy caps, here we're doing something a little bit more, I guess, descriptive instead of prescriptive. I'm not sure if that's the right way to describe it, but what I'm saying is we were simulating hypothetically if you had 50% of 2019 mobility at religious centers, and then you had like 100% of 2019 mobility at gyms, and then say 0% of 2019 mobility at retail. What does our model predict would happen under that? Instead of saying, if you as a policymaker set up a maximum occupancy cap, this is what's going to happen. And so this was like basically taking a step back from the claim and being like, we can tell you what our model says under these hypothetical mobility plans, but it's up to you to figure out how do you reach these target levels of mobility if that's what you want. And so this still does allow you to see, differences in what is the cost of 50% of essential retail versus 50% of retail. So you can see the heterogeneity across different POIs and play with that a bit. But it's not saying as prescriptively like this is what would happen if you this is what you should do, or here are like the different maximum occupancy results. And so those are two major ways that we changed since the original paper. Like the use case is slightly different, and we added these bars. And I think that's what was more useful and also more faithful to what they needed. In terms of how they actually used it, we gave it to them. Like there are a lot of political factors at that time around reopening. They weren't able to tell us like, oh, because of your dashboard, we did this. But I think definitely we did see some sort of like heterogeneous plans come out where it wasn't just total lockdown or total reopening. We did work with them on a separate project afterwards where we did get more feedback, and that was around vaccine site distribution. And so there they had a budget of mobile vaccine sites that basically carry like the Johnson & Johnson vaccine. And they wanted to know, where should I physically place these sites? And because they knew we had worked with mobility data before, they were thinking maybe the mobility data could be one way to inform the placement. And so maybe place the sites at places where there's already more activity, like near a grocery store that everybody already visits. And then we did this also paying special attention to under-vaccinated communities, like Black and Latinx communities. And so once we did this, they were able to give us back data that said how many vaccines were administered at each site. And we could see that the places that we recommended had higher rates of, like had more vaccines administered compared to places that were far away from what we recommended. So that's somewhere where we got a little bit more feedback on.
That's awesome. Is that published? That last bit?
Yeah.
That
It's in
vaccine.
I can send
the
it.
Vaccine locations and stuff like that.
You can find it on my website, or I can send it if you can't find it.
Cool. All set. Thanks very much. Like awesome stuff, as I said before.
Thank you.
So thanks
so much.
for coming.
All right. Well, with that, I think we should thank Serina again virtually. I'll give I can do a real clap because I'm unmuted. Thanks so much, Serina, for coming. And thanks to everyone for attending. And this was our last seminar of this term, so we'll see folks back in Michaelmas, so in, I guess, October of next year. So have a great long summer, and nice seeing you, Serina.
Yeah, nice seeing you too. Yeah, I'm actually going to be back in New York, so maybe.
Oh, great. Yeah. Cool.
All right. Bye.
Are you switching jobs? Is that?
No, my family's in New York, so I'm
Oh,
doing
okay.
my talk from New York, and then still deciding where to start as an assistant professor. But I'll be starting that in July 2025.
Very cool. All right. Well, see you around then.
All right, see you. Bye.
Bye-bye.